So I'll be speaking today about universal approximation or probability measure valid functions. Okay. So to motivate our structure, we'll consider the following problem from mathematical finance. So suppose you have a large number of options written on a large portfolio, and you want to model it without making almost any assumptions on the underlying dynamics, right? So that involves computing a large number of these quantities, where the V's are the terminal payoffs, XT is the price process of our d-dimensional asset. These are very large, corresponds to the number of assets in our portfolio. Q is a risk neutral measure. These are time horizons, and these are the initial states. So you want to compute many of these quantities, right? So that seems like a very natural venue for machine learning, right? And why is that? Well, everything's high dimensional, and we just really want to approximate this function seemingly, where it takes the initial terminal time, initial state, initial time, and initial state, and it maps it to the very large vector of all of these possible payouts for these payout functions, right? So this seems like a great idea, and actually this function is learnable by like a deep feed-forward network. So what's the issue? Well, there's two issues that we come off right away, which is the first is if sometime we want to re-add a new, we want to add a new option to our basket, a new type of payout, we need to retrain this entire model. Of course, it's not convenient. Second thing is the word learning here is a bit used vaguely, because even though if you learn this function, we don't actually learn anything about our price process, its behaviors, dynamics, anything really, just some specific evaluations against some specific test functions. So really not learning much about the actual dynamics of the underlying price process. So somehow this is not really learning. So how can we do this while not having these problems? And so the solution actually comes by considering a different perspective, or basic perspective on this quantity. Namely, we represent these conditional distributions as integration against, these conditional expectations as integration against a regular conditional distribution. So nu t here stands for the conditional law of xt time t given initial state x at time 0. And so here we suppress now the initial time for simplicity. So the idea is if we're able to learn this function or approximate it weekly, then we should be able to solve this problem and we avoid these issues. Now, why is that? It's because once we learn these marginals, we're actually learning things about the dynamics of xt. Moreover, so we don't have the second problem here, we learn something about the price process. Moreover, every single time we want to train a new option, we simply need to sample these measures and just do Monte Carlo. That's very easy. So just perform this little quadrature here. That's so now it's simple. We don't have these issues, and there you go. But now we have a new issue, which is how do we approximate such a measure-valued function? So this is sort of the subject of the talk. So what does it mean to approximate? Well, this talk, we just, before I say that, we'll have one assumption throughout, and it's just the fact that this function is a function of t and x into the Weierstein 1 space here. So it gives an initial time and initial state and passes the conditional law. This is continuous, so continuous with respect to the Weierstein topology here. All right, this is a very weak condition. In fact, if nu is the conditional law of any SD with uniformly Lipschitz drivers, so any classical model, this is satisfied, right? So this is a very weak assumption, totally generic, covers all classical models without jumps. Think about the jumps case at least. Okay. And if we want to approximate things uniformly, this is sort of universal statement. We want density in such a space. So we need to fix a compact for technical reasons. So the input will consider our approximations on a compact, at least for the moment. And if we want to talk about approximation, we need a metric on the space of functions, right? So these are continuous functions from compact, non-empty subset of R1 plus D to the Weierstein space. So the metric is going to be the usual uniform convergence on compacts, distance generating metric, and that one is the following. So now the uniform distance is not Euclidean, but of course it's Weierstein, where the uniform worst case scenario quantification is for all times and all initial states. Right. So why is a good choice of metric? We should at least motivate it. It's because of course it controls the worst scenario error. So if this is the target and this is our model, we bound this by epsilon. That means we've bound the worst case scenario by epsilon, and potentially better case scenarios can be better. So this is sort of a very strong notion of approximation. But from the topological standpoint, it's very weak because sort of this the topology generated by this metric, sort of so-called compact open topology, sort of the weakest topology that has reasonable good properties. So it's very strong and very weak from the approximation theoretic and then topological views, respectively. Their natural choice. Okay, so it's not really ad hoc. So, okay, so let's consider the models now. So what is going to stand in for the new hat in the last slide? So we're going to introduce a new family of deep neural models and give some examples. So there's going to be two sort of meta parameters or to choose from. The first one is we fix a dense family of the Wasserstein space. Okay, so this is not a dense family of the spaces, not a dense family of the functions of the Wasserstein space. Of course, that'd be a bit much, but just a dense family of the actual Wasserstein space, just on the image. Okay, and we fix an activation function, right? So a continuous function on R. So typical feed-forward networks only have this as a meta parameter. We have one, of course, one new variable. Okay, so what our models look like? Well, they look like this. So what's going on here? The new hat takes a terminal time, initial state, and it maps it to this, this mixture of these mu's. Now, what are the mu's? Mu1 hat to mu n hat are just members of our dense family. F hat is the classical feed-forward network, right? So it's this factoring function composed of the activation function, which is applied component-wise. So the black dot means component-wise composition, and you do this ad nauseum for some finite amount of times. So this is that. And then finally, we have this softmax function. The softmax function is just something that takes an n-dimensional vector and maps it to the n simplex, right? So returning to our models, what's going on? It says we have these n measures that we fix, these n probability measures, and our deep neural network is learning, or should be learning, to for every single terminal time t and every initial state x, it should be learning to remix those in an appropriate proportion so that new hat at that for that time and state is close to new, right? So an idea is that basically that. Very simple to explain. In other words, you can say it can also be viewed as classifying kind of which of the new n's is closest, which of the mu n hats is closest to new at any single time and state. Okay, great. Okay, so that's very abstract. Let's give some concrete examples. We can relate this to GANS. So just speeding along quickly, if we view this dense family D as being the following. So you fix a probability measure in RD and you push it forward with all just vanilla classical feed-forward networks. These are what are known as GANs, generative adversarial networks. And in the paper, we show the folklore that they are dense. So they're dense in the first Wasserstein space. And this is just what this says here. So in that case, if you just plug in the push forward of fixed measures, say for example, Gaussian on RD by DP4 networks, different ones, and plug those into the mu n hats, where the D, right, oops, right, these guys, we replace these guys with GANs. Then our model, our very general class of models looks like this. In this case, this is the following things, is that you can find n feed-forward networks, which push the Gaussian distribution on RD to some probability measures on RD. Then for every single time and space, I have another auxiliary feed-forward network, which gives me mixture coefficients. So because of the simplex here, softmax the simplex. And it says that you can mix these GANs depending on state and time, and this should be able to approximate everything. I mean, this is the hope in the next page, next two pages. Okay, another example of our model is comes from quantization. So quantization is the idea of taking some infinitely complicated object, namely the probability measure, and reducing it to some finitely complicated object, namely an empirical distribution. Right? It's well known that that's if the probability distribution has just a bit of integrability, then you can always find some finite point masses and q of them, such that it's this close in Wasserstein distance. So this is sort of the best. This is the optimal estimate that's known. I mean, the optimal estimate. And so whatever. Well, the important thing is then that means that we can approximate. We can replace these mu n hats with empirical measures. And by doing in the previous model, and by doing so, our general models look at the following form, which is actually quite interesting. It says that you can mix n different empirical measures, each with nq points of mass, and you should be able, and that mixture depends, of course, on the time and state. And by doing that, you should be able to approximate, at least the hope is, any probability measure value function from time and state to the Vashtian space in RD. Right. Let me just point out one interesting point here is that here we're not saying we're not mixing n times nq points with on a very large simplex. Here we have a very small simplex of consisting of with n vertices, and each of these vertices is a finally supported measure with nq points. Right. So those are some examples of our probability measure value models. So, but what does the approximation theorem say? The approximation theorem says that if your activation function is reasonable and D is just as we described before, it's a dense in this Vashtian space, should be 1 here, then for every measure valued function, given epsilon that satisfies some basic, which is small enough, then you can find some U1 and UN hats inside this dense family of probability measures D, such that are one of our models, okay, F is a feed-forward network with activation function sigma, is uniformly epsilon close in this uniform Vashtian sense to the target function. Okay, so in other words, this class of models here is dense in that function space I described earlier, this particular one here. All right, this is a qualitative result. Qualitative results are nice, says we can do something, but quantitative results are, of course, nicer. They tell us, can this really be done in practice, or what does this mean? How many parameters do we need? So in the notation in the previous slide, you can actually do the following thing. If nu is uniformly continuous, then we can actually describe all the parameters or bound them. But we know that the number of points we need in this high dimensional simplex that we're mixing with, of course, is proportional to epsilon, and this is the proportion. Omega here is the modulus of continuity and of the function nu we're approximating. So of course, more irregular functions may need more points, totally reasonable. And D is the dimension of the input space, again, totally reasonable. Now, F hat is a neural network of width at most D, almost this width. So in other words, it's sort of, in some sense, bounded and is a function of a nu and therefore a function of epsilon 2. So the regularity is really propagating through the entire construction, makes total sense. And then lastly, if sigma is a non-polynomial off-holder function, then F's depth, so how many layers that deep feed-forward network has, which describes the mixtures of these n measures mu n hats, is of this order. That's really big, but of course you get nicer estimates depending on if sigma is nicer, and that's in the paper. Okay. So really have the complete description of the complexity of these neural networks. So lastly, let's just say that, of course, you can extend this to Borel functions using a Lucent type argument over the entire input space. And there's more general examples in the paper, so on, or cases. Let me just circle back and finish off the discussion by relating it back to our motivational question. So if you have two random vectors on an auxiliary probability space, they're random vectors with taking values in some Euclidean spaces, then for every epsilon bigger than 0 but smaller than 1, I can delete a subset of my input space, so a space on which I'd be conditioning on. So, and I consider all the y's which I condition on inside k epsilon. Then I can say the following sort of approximation result with the quantitative estimates of the previous slide that says that on k epsilon, I can approximate this regular conditional distribution uniformly to epsilon precision using one of our models, complexity given in the previous slide. Moreover, k epsilon is a set of arbitrarily high probability, which I can choose by setting epsilon of the input space. So in other words, I can really get sort of a uniform, really nice approximation error, and I can basically approximate any regular conditional distribution I want. Using one of these models, examples are in the previous slides. Okay, corollary. What about conditional expectations? Well, if f is uniformly Lipschitz in its first argument and uniformly bounded in the second, right? Then, so f is a function of x and y, the notation of the very last slide, then I can approximate uniformly on k epsilon this conditional this conditional expectation. Yeah, and the only difference is that now my error scales up by some constant m that depends only on f, depends on nothing else, not dimension, not the k epsilon, nothing else, not on epsilon, of course. So in other words, with the same order of approximation quality, I can then do exactly the same thing, but when I can test against any reasonable function, Lipschitz in the first argument, uniformly bound in the second, I can approximate this conditional expectation against that regular conditional distribution to n times epsilon precision for some absolute constant n. Okay, so conclusion, what's gone down? The conclusion is that we introduce and give the first universal class of measure value deep neural models, at least provably so. Our architecture is like our framework is extremely general and covers most architecture, like a very large number of architectures, and it's applicable to many problems of mathematical finance. Essentially, we show we can universally disintegrate. In the paper, we have universal approximation guarantees for GANS, mixture GANS, and all kinds of other models, mostly just to construct particular examples of our architecture. So there's sort of propositions. And actually in the paper, the results hold for significantly more general input and output spaces. Yeah, so like Polish output spaces and so on. And yes, and in the paper, last thing is a sort of mathematical point of interest. You'll see a new type of proof technique for showing universal approximation in infinite dimensional spaces, and uses approximate metric projection type results. So pretty cool stuff. Anyways, thanks a lot for listening to my talk, and hopefully we'll see each other in person.